Hi. So today, we're going to be talking about building a global scale data platform with Kubernetes, MongoDB, and a couple of different HashiCorp tools. As he mentioned, my name is Dan McKean. I'm a product manager at MongoDB, and I'm joined by Hantzaras, who is my engineering director counterpart. Together, we're primarily responsible for enabling our customers to run MongoDB on Kubernetes.
So today's talk is focused around building highly scalable, highly resilient data platform, leveraging Kubernetes' capabilities to deliver multi-region, multi-cloud resilience using Kubernetes operators, HashiCorp Vault, and Consul. So we're going to be talking about why you might decide to self-host, how Kubernetes can help, and some of the challenges you might face along the way. And then we're going to look on how you can solve those challenges using those tools.
So no matter how many use cases can be met by fully managed services running in the public clouds, like MongoDB Atlas, there's going to be some workloads that can't be run entirely with software or platform as a service. You might want complete control of your infrastructure to tune and optimize the hardware, or to manage networking and security. You might want to avoid or mitigate the extra costs that can sometimes come by using cloud services. For example, if your load on your application is incredibly stable, you might not want to pay for the ability to scale at a second's notice. Or you might need data to reside somewhere that's not supported by your cloud provider or even by one of the cloud providers, or need to meet specific compliance requirements. But there are reasons why more and more companies are looking at running services across hybrid combination of public and private infrastructure. So you can benefit from higher resilience and redundancy. It's not totally unheard of for an entire cloud provider to have an outage. Sorry, do you mind scrolling down in the speaker notes? Cool. Hybrid or multi-cloud can help to avoid vendor lock-in. And it also can mean that you might possibly be in a stronger position to negotiate prices with any cloud providers that you do choose to use. Sorry, this clicker seems to be scrolling through the speaker notes now. It's still doing it. Cool. So nothing worth having comes for free. So whether it's across multiple clouds on your own infrastructure or some hybrid approach, self-hosting or running things yourself means that you are taking on more responsibility for running and maintaining the services than you would if you'd been relying just on a single cloud provider. So teams need to manage the different environments and varying infrastructure setups, and this can make it hard to maintain consistency. Obviously, HashiCorp has some great tools to kind of address that, but there are still cases where you need to self-host, and those tools can help there to a certain extent, but there's still some considerations around that. And this can theoretically worsen the developer experience, especially if you don't establish the sort of abstraction from having to deal with the different configurations for the different architectures, for their different interfaces and infrastructure. And this leads to the importance of centralized DevOps to enable developers and reduce cognitive load for those developers in their day-to-day lives.
So you kind of already know we're going to be talking about Kubernetes, and we're not going to pretend like all of those problems can be magically solved. So Kubernetes offers a common infrastructure layer that is cloud agnostic. So whether you're using public clouds or your own data centers, you can have this consistent infrastructure interface that Kubernetes provides. So you can use that in order to deploy your application in the same way wherever you are. And this is kind of a key benefit in all different kind of hybrid environments. Kubernetes shines when it comes to automation, like with features like auto-scaling, load balancing, self-healing capabilities. It helps you reduce and automate a big part of the operational burden. Teams can automate much of the infrastructure management and integrate that in automation tools, your CI/CD pipelines, and so on. And by using Kubernetes, you can also increase resilience of your application. So within a cluster, Kubernetes handles monitoring, and if you need to kind of replace lost pods, it kind of handles that by default. And it can also handle larger failures, like losing a whole Kubernetes node, and you have kind of minimal destruction doing so. So there are a lot of different flavors of Kubernetes, and since we're talking about hybrid deployments, you might think of deploying OpenShift on-prem or EKS or AKS on the cloud, and you kind of want to work with those together. The good thing is that there is the CNCF conformance test where you can rely on those, and you know that if one Kubernetes distribution is conformant, then it can kind of it can interact with others without any problems. Now, if you're running it yourself, you might use your own infrastructure or use cloud services. And in that case, you can kind of use the same flavor anywhere. Now, there is kind of a balance between customizability and convenience. So you can self-host and have as customizable as a Kubernetes deployment as you want, but also then you can have the convenience, I made it, to use a Kubernetes as a service offering in the cloud, but then you might not have access in the Kubernetes control plane. Yeah, and this flexibility kind of ensures that in hybrid environments, you have consistency of how you run your application, and you have this portability to move from one environment to the other. So now there's something that has changed lately. We used to, a few years ago, we started focusing on scaling up Kubernetes instead of scaling out our clusters. So we were thinking of, you want one large cluster instead of multiple small ones. I'm going to have one large cluster for all of my production applications. Now we're trying to have smaller Kubernetes clusters, single clusters for different environments, different applications, and so on. And we're moving from treating our clusters from pet, treating it as cattle. There are a few different reasons for that. One, which is quite relevant here, is that so a single Kubernetes cluster has latency requirements, so it cannot span regions. So we're running applications across multiple Kubernetes clusters becomes very relevant. And of course, that comes with a few key considerations. So regardless of whether it's on the cloud, on-prem, hybrid, connectivity is a very important aspect. So you need to ensure that services across different clusters can communicate seamlessly. And this often means leveraging solutions like service mesh, like we're going to show in a bit with Consul. Equally important is security. So as you distribute applications across clusters, you have to ensure that you have secure communication, whether through encryptions or VPN. So you also need to maintain consistent security policies across those different environments in order to avoid vulnerabilities.
So now we've talked a little bit about why you might be self-hosting, regardless of whether it's in public clouds or private clouds. And we talked a little bit about how Kubernetes can play a part to help that. And we've also talked about some of the challenges. And we're going to talk through actually addressing those challenges and kind of how you might use some of the HashiCorp tooling in particular to do that. So we're going to start by looking at this example architecture. And at the moment, it's super basic. We've got 3 Kubernetes clusters represented by the horizontal boxes. And you can see each of them is running a different place. We've got cluster 1, OpenShift running on-prem. We've got cluster 2, which is a GKE cluster. And we've got cluster 3, which is using Rosa, a Red Hat OpenShift service on AWS, We kind of picked the public cloud entries at random, and I didn't want to add a fourth. Then we've got different things running. Each will be running with high availability. We've got different things running in the clusters. Each of those things will be running with high availability across the 3 clusters. So we're going to have HashiCorp Consul. That's going to provide the cross-cluster connectivity for all the workloads to depend on. Next to Consul, we're going to have Vault running across the 3 clusters, which it will be managing our secrets and sensitive data. And lastly, taking up the most room, we're going to have MongoDB. And we'll get into a little bit more about what that actually is a little bit later. And we're going to tackle the setup for each kind of in order now.
So we're going to start with Consul. So this is HashiConf, so hopefully you've all heard of Consul before. If not, probably you can leave at this point. So Consul supplements Kubernetes with some capabilities that align perfectly with the challenges that Dan presented earlier. So first of all, service discovery. So we can automatically track which services are running and where they are, even across different clusters, and make them accessible to each other. And then Consul Service Mesh provides secure connectivity within and between the different Kubernetes clusters. So this all fits perfectly in the architecture that we are going to be describing. So Consul connects our hybrid setup securely, and this enables resiliency and redundancy even if we lose a whole cluster. Consul handles the complexities of service discovery and secure communication, reducing our management overhead. And we also improve our security, which is kind of like secure connectivity, as we mentioned before, is a critical factor for hybrid setups. So let's slowly dive a bit deeper in the technical stuff. This is how we're gonna set up Consul to run in Kubernetes. First off, we have to set up RBAC, role-based access control for Kubernetes, to give Consul the permissions that it needs. So in the top half, we're defining a role with permissions to interact with Kubernetes resources like pods, services, endpoints, and so on. And then in the lower half, the service account is associated with Consul clients. And kind of these are going to be running in the clusters, and they're going to the service account is going to assure that only authorized Consul agents have access to the Kubernetes resources. So similar to this, RBAC needs to be applied in all of our Kubernetes clusters in our setup. And then to actually install Consul, we're going to use the Consul Helm charts. So what we're seeing now here is the Consul values file. So at the top, we see the global configuration. Data center shows us just the identity of the cluster that is going to be running. Enable federation tells Consul that each of the cluster connects together and enables advertising services into the other clusters. This is really critical for our setup. This supports bidirectional communication between members of an application. In our case, the different replicas in a MongoDB replica set are going to be using that to communicate. On lines 5 to 11, we actually set up Consul clients and servers. And between them, they handle service registration, service discovery, and communication. On line 11, the connect equals true enables Consul service mesh functionality. And then on line 12, we enable connect inject. That means that Consul will automatically inject a sidecar proxy into every pod in our cluster. And this proxy will be tunneling communication via Consul, enabling service-to-server communication via the service mesh. This is also a key part to simplify service connectivity across different clusters without having to do any changes in our applications. In our case, this helps MongoDB pods communicate seamlessly across different clusters to each other in order to build the replica set. Now, on lines 15 to 21, we enable the mesh gateway. So the mesh gateway allows different Consul data centers, in our case, different Kubernetes clusters, to route traffic between them. So each cluster's mesh gateway handles cross-cluster traffic. So we've got 2 per cluster for high availability in this case, and you can see that on line 17. And then on lines 23 to 29, we finish with the federation settings. So for each cluster, we specify the IP address of the other service mesh gateways for the other 2 clusters, allowing them to form the federation. So as you can imagine, this is used to set up our Consul, to deploy Consul, but we also need some information for the other Consul deployment. So you probably understand there is a cyclical dependency here. There are 2 ways around this. Either you can control the DNS entries for each of the mesh gateways and introduce them in the federation settings and then apply the Helm charts, or apply the Helm charts and then go back, apply the Helm charts, leaving the federation settings out, and then going back, adding it and reapplying the charts. Whichever options you do, it's pretty straightforward with the Helm charts. So now moving on to setting up HashiCorp Vault in a multi-cluster environment. So Vault provides secure secret management for data like API keys, passwords, certificates, database connection strings, anything like that. So Vault is particularly useful in this environment because it has, so native Kubernetes secrets are base64 encoded and not encrypted at rest by default. So this makes them vulnerable. Vault secrets are not only encrypted, they can be tightly controlled with access policies, and Vault also handles secure distributions of those secrets. So Vault is valuable for any type of sensitive data. In our case, we're going to include database credentials, and Vault is going to handle the secure distribution of those secrets across all of our different clusters. So to deploy HashiCorp Vault in multi-cluster resilient setup, we're going to run a Vault server in each of our clusters. Vault uses RAF for leader election across the different clusters. So in much the same way as we did with Consul, we're deploying Vault to each of the clusters using the official Helm chart, and each cluster will have its own values file. Okay, so on line 5, you see that we are enabling high availability. So Vault will automatically hold the election when there isn't a current primary. In this setup, each Kubernetes cluster only needs 1 Vault replica. So you can see that in line 6, we set replicas equals 1. But those will automatically be part of the same logical Vault installation. On lines 8 to 14, we're setting up Raft. This is the heart of the high availability. The node count aligns with the total number of Vault instances. So although we have 1 per cluster, here our total node count is 3 because we have 3 clusters. The retry join section on line 12 sets the address for the other 2 members of the Vault setup. In this case, we're using Consul service mesh for the connectivity between Vault members. So you can see that the address we're using are for the services created in the other Kubernetes clusters for the Vault service running there. On line 15 and 16, we are creating this service for Vault running within the cluster. And then on 17 and 18, the Vault address tells the local Vault clients, like the Vault CLI or the Vault server itself, where to find the active Vault leader. And the injector at the end automatically injects secrets into Kubernetes pods running in each of our clusters. So for both vault address and the external vault address, you can see that the address is the vault leader service. We could have used the local vault service, but using the leader is critical because that is what assures high availability in case we lose the local leader. Okay, so to enable the vault leader DNS entry, we need to do 4 things. So first, we add this extra configuration to the end of each of our Consul Helm values files to make Consul track which vault server is the leader. Oops. Okay. And then each vault instance needs to be registered as a Consul service. So we add this configuration to the end of the Helm of each Helm values file of each of our vault deployments. This registers each vault instance as a service named vault and turns on the health checks to identify the leader. And then next, we run this Consul CLI query, and this creates the leader DNS entry. Thanks to the health checks, this routes traffic to the vault leader. Now, in reality, you would probably add this extra configuration for vault and Consul from the start. What we just wanted to walk you through those dependencies. The last thing to do is to ensure that Consul DNS is actually accessible to normal DNS queries within the clusters. The easiest way to do that is add Consul DNS as a secondary zone for core DNS, which is Kubernetes' default DNS servers. Instead of using the IP address of a single Consul client and server, which wouldn't be resilient, we create a Kubernetes headless service called Consul DNS. Setting cluster IP in line 6, setting cluster IP equals none makes the service headless, and then queries will be routed in a round-robin fashion to the pods that match the selector. In this case, that's Consul's clients and servers. And then once the headless service is created, we modify the core DNS config map in each cluster to forward DNS queries to the Consul DNS via the new service. Now, the advantage of adding Consul DNS as a secondary zone is that we don't have to interfere with the default DNS in each of our clusters. Now we have full high availability for Vault across our 3 different clusters, and we can begin managing secrets. Now, we're not going to go really deep here, but there are a few different options. Secrets are created and managed through either Vault CLI, UI, or its API. For example, to create a secret for our database user password, you could run this CLI command. Secrets can be stored under specific paths. In this case, it's the secret/DB credentials, and policies define which applications or service accounts can access those paths. And then in order to inject that secret into a pod, we would just use those annotations in our pod. Firstly, the Vault policy associated with the role determines what secret can be accessed. The path at the bottom selects the secrets, and then the selected secrets are delivered to the pods as environment variables or files in their decrypted form.
Cool. So we're from MongoDB. We're going to use MongoDB as the kind of the workload leveraging this multi-cluster support. MongoDB is known for being a document database rather than a traditional database. So very, very briefly, that means that the data that's accessed together and used together is stored together. Far fewer joins, much easier schema changes to evolve your data alongside your application. And there's a number of other strengths, and I'm going to kind of whip through these quite quickly because we're doing badly on time. MongoDB is fantastic for resilience. It has replica sets that replicate data across a number of members. So you've got high resilience to failure. One member in each replica set has write capabilities. But we also have sharding, which provides kind of horizontal scalability. So shards hold different data, and that can be manually controlled, or it can just be distributed evenly across the shards. And each shard has its own write member, so you can scale both read and write capabilities horizontally. And this works really, really nicely with a multi-cluster setup. Kubernetes operators are kind of one of the highlights of Kubernetes extensibility. And they extend the default control plane of Kubernetes to support the custom logic of a specific application. So in our case, our enterprise Kubernetes operator manages running MongoDB in Kubernetes and saves you a lot of the kind of toil of doing so by provisioning stateful sets and persistent volumes. You define resources as custom resources, and it really simplifies day 2 tasks like upgrades, where a change to a value means rolling restarts without any impact to your application. And we, over the last 2 years, have built the ability to deploy across multiple Kubernetes clusters with replica sets, as I mentioned, which are kind of the basic high availability deployments. Ops Manager, which is our management server, it's used for kind of advanced backup capabilities as well as monitoring and some kind of data plane automation. And more recently, we're very excited to have support for multi-cluster sharded clusters. That always trips me up, the number of times I mention cluster in a given day. Across multiple Kubernetes clusters for this high availability and scaling of write capabilities across multiple locations. So what I'm going to whip through quite quickly is this architecture. We've got the operator installed, and it's in the top left in cluster 1. And then what we're effectively going to have is a sharded cluster with 3 shards. A really nice scenario for this might be if you're in a long, thin country, say Italy, and you've got a northern region, you've got a central region, you've got a southern region. One shard could hold the data for the northern, one shard could hold the data for the central, and one shard for the southern. By having the right members of each shard located in the right region, you minimize latency. But you also get high availability across the regions. So loss of one of these clusters or regions will kind of, you'll still have that availability. And then we've got config server and MongoS. MongoS is the router that provides access to the shards and the different data in the different shards. And config server is just a simple replica set that kind of manages the data that's used for that routing. So very similar to when you set up anything in Kubernetes, really. We've got the RBAC. It's relatively simple. You can set it up manually. And we also need a kubeconfig secret installed alongside the operator. And that kubeconfig secret is what actually gives the operator the credentials needed to call the API server of the independent Kubernetes clusters, and what allows us to run replica sets and sharded clusters in those clusters. But we do have a kubectl plugin. You can see the command for it there. It makes those 2 steps much, much easier by setting up the RBAC for you. One of the nice things is it pulls the CA data, the certificate authority data, and the token from each of the service accounts, and puts it into the kubeconfig secret. So it automates a lot of stuff for you. And then actual installation is really simple with a Helm command. I'm kind of whipping through things relatively quickly because we really are running short on time. But you can see that it's relatively simple. And then for the actual deployment, kind of the key component is that you define the basics, like the version of MongoDB that you're going to use. You provide it credentials to Cloud Manager or Ops Manager. They're both different options for our management server. Cloud Manager is just hosted by us, but still supports on-prem deployments or self-managed deployments. And Ops Manager is the self-hosted management server. But the more interesting bit is that you can actually get into defining these shards. So you've got the default configuration for each shard at the bottom there, where we've got a priority of 20 for the member that's in cluster 0. Sorry, should have renumbered the clusters. The top cluster. And so we've got the primary for each sat in the top cluster there. Wouldn't work very well in that Italian scenario I gave you where you want different primaries in different regions for different latency or for minimizing latency. But you can override on a per shard basis, which makes this really, really flexible. And you can override the priorities and also how many. So say shard 0 there on the far left has the most data or the highest need for resilience. You can have duplicate secondaries in, say, 2 of the regions and end up with 5 members of the shard. And you can also control where the primary is. So in this case, we've put the primary in the central cluster, which might equate to the central region in the scenario we mentioned. You can also override the configuration for the config server and the MongoS, but typically you just want to make sure you've got resilience for both across all of the clusters because they provide the routing capability to the data in the shards. Using MongoDB is then just a case of setting up database users, connecting your application, probably setting up TLS in most cases and setting up backup. but we were kind of more interested in the infrastructure use cases of establishing multi-cluster connectivity and high availability and resilience. So we've kind of not gone too much into that. And then wrapping up, you end up with a very highly resilient hybrid on-prem and multi-cloud setup. You've got Consul Service Mesh providing the connectivity. Vault is helping with the secret management. And you've got a highly resilient and very scalable MongoDB deployment. And we are ever so slightly over time by seconds. But thank you very much. You can find more information via this link or this QR code. And we'll stay in the corridor for a little while if you've got any particular questions for us. We're not experts on HashiCorp products, but we will try our best, and we can certainly answer any MongoDB questions you might have. Thank you very much.